identity, the Hello and welcome back to my channel. If you haven't subscribed yet, please do it. Also, welcome back to myself too, because it's been a minute. Last time we talked about matrix multiplication. Yeah. Today we are talking about different types of matrices. After that, a very own property of square matrices, which is the trace. What we mean when we're talking of square matrices. Matrix that has the same number of rows and the same number of columns. We used to call M and N the number of rows and the number of columns. So for us, that means that M is equal to N. Today is the first day of March already, and it's too hot. I cannot imagine what's gonna be like August or July. And I'm not a big fan of summer, so I wrote down an example of a square matrix. And first of all, well, of course it's a 3 by 3 matrix, so M is equal to N, and on the main diagonal, which is this one, we have entries that have the same column number and row number. So 1, 1, 2, 2, 3, 3. This is the first thing to remember about square matrices. And let's now dive a bit deeper on the different types of square matrices. So let's get going. The first type would be the diagonal matrix. This is an example of a diagonal matrix. All entries are equal to 0 except for those which are on the main diagonal. And yes, they can be negative, they can be a ratio, they can be anything, but they have to be different from 0. They could be a square root, for example. In the family of the diagonal matrix, we have then another type of matrix. We usually call it I for identity, and the N stands for the number of rows and the number of columns, because again, let's keep in mind we're talking about square matrices. N is equal to 4, so this will be a 4 by 4. The main diagonal will be of ones, and we have 0, main diagonal, the special case of a diagonal matrix. Identity matrices are like parsley. You can find them anywhere, mostly because they have a pretty useful property which makes them very usable. The algebra field, algebra gang, I don't know. Anyway, that goes also for econometrics and statistics, and that's it. I cannot think of anything else. The rule I'm gonna talk about is this one. Any matrix A then we also have an identity matrix. The solution will be A. How? Let's give an example, because it's not magic, so we can figure that out. We know damn well that our identity matrix will have zeros around the main diagonal and will have ones on the main diagonal. Let's figure out what dimension our identity matrix should have. We want to multiply them, right? And we know that we have a rule to multiply two matrices. If you remember the rule of row by column multiplication, then you should know that if this is our m by n, the second matrix should be a n by something, right? Because it needs to have the same number of columns of the first matrix and the same number of rows of the second matrix. So basically we already know that this has to be a 2 by, but this is also identity matrix, so a square matrix, which means that this has to be a 2 by 2. We have found our identity matrix, and now we can proceed and do the multiplication. Our identity matrix will look like this: 1, 1 on the diagonal and 0 outside. Let's see what the solution is. So we have 3 by 1 and minus 1 by 0, so 3. First of all, this is a 3 by 2 and this is a 2 by 2, so the solution will be a 3 by 2. So the same dimension of this one. Let's go on. We can actually confirm that the identity matrix, when it's multiplied by any matrix, will give you the same exact matrix you started from. If you keep studying these things, at some point you will come across the identity matrix again. Let's just cut the BS and let's go on. A symmetric matrix is the transpose of itself, but since we haven't talked about transposition yet, we can also use another definition that it's a bit easier and that it's perfect now because we haven't talked about transposition yet. Symmetric matrix looks like this. This is an example of a symmetric matrix with respect to the main diagonal. The elements outside the main diagonal are symmetric. And I mean, this is true. See, formally, we can also write it as J is equal to A Ji, because, for example, let's take 1, 3 is equal to A 3, 1. Let's verify this. A 1, 3 is equal to A 3, 1. Yes, equal. Almost forgot, but for example, a diagonal matrix, so the one with the 0 outside the main diagonal, that one is also a symmetric matrix, and that's because zeros are equal to zeros. So you have the main diagonal and on it you have any number, but outside it's all 0, and those are equal. So yes, that is a symmetric matrix. We also have two more types of matrices, which are actually not that known. They are absolutely mistreated by matrices users, I guess. I will have now somewhere, I'm not really good at editing, so I think you know by now that I'm not really good at doing it. So I will also try to put a small clip to show you how many different types of matrices there are, and probably that will be taken from the Wikipedia page, because, you know, basic B. Last but not least, actually they are least, triangular matrices. I haven't really figured out how defining them is useful. A and B. A and B. Great. I will 3 by 3. Yeah. 3 by 3. Great. These are the very discussed only by me triangular matrices. And why do I look so red on my face? Lower triangular matrices. And this is upper, ugly, upper triangular matrix. Basically, what's the difference? Well, this is the main diagonal and this is the main diagonal. As you can see, we have a triangle up here made of zeros. So a lower triangular matrix will have zeros above the main diagonal. And that sounds counterintuitive, as lower you would think that the zeros are under the main diagonal. I don't know what they're doing that. On the other hand, the upper triangular matrix has the 0 entries below the main diagonal. And yeah, it doesn't make sense. You know that probably upper is referred to the non-zero entries, but it would be easier to say upper and think of 0 entries, right? But no, we're done with the types of matrices that I'm going to talk about. The trace is the sum of all the entries on the main diagonal. This is also a peculiar thing of square matrices. Voila! This is the formula of the trace, and it's really easy actually. Trace, it's just called TR. So this is the name of the matrix that we are calculating our trace of. This is a summation and it goes from 1 to n. N is the number of rows and columns. So what we basically are saying is that we are going to sum all of the entries on the main diagonal until the very last element of the matrix. And we know that we are talking about the diagonal because, as we said at the start of this video, I think, the entries of the diagonal have the same index. So we have A11, A22, and so on. Last one will be ANN. Since we are only interested in the main diagonal, for this example, I was lazy. I choose to use 0 outside of the diagonal. Trace of A will be 1 plus 1 over 2 minus 4. So this is A11, A22, A33. Exactly what we were saying here. Over 2. That's a 2. This is the trace of this matrix. Trace properties are absolutely easy, so I am just going to write a list. The trace of a sum of matrices is equal to the trace of the first matrix plus the trace of the second matrix. Second, the trace of a scalar multiplication of a matrix. So we have a scalar by a matrix is equal to the scalar that multiplies the trace of the matrix. Third, the trace of A is equal to the trace of the transpose of that matrix. I know we haven't talked about transposition yet, but this is quite easy because when we are transposing matrix, we are actually rotating the matrix, but with respect to the diagonal, that doesn't change. So basically the trace is all about the diagonal, which means we don't really see any change in that because the diagonal is still the same even in the transpose. The last one is actually very cute. It says that the trace of a identity matrix of dimension n is equal to n, and that is because the identity matrix as the entries on the diagonal are ones. So of course, if you are summing all the ones on the diagonal, you will end up with exactly the number of rows and columns of the diagonal. So the trace of an identity matrix is equal to its dimension. Easy breezy. I am actually done. I have finished. It didn't take as long as I thought this would take. Maybe I forgot something really important and now I can't think about of anything that I'm forgetting, but maybe I am. I don't know. Thank you for sticking with me again. Let me know if you have questions about anything. You can write them in the comments and you can also subscribe. That's for free. So thank you again. See you soon.